cool.
So this event is brought to you by IEEE and Branch and by UQCS. So if you want to find out more about either of our branches, feel free to have a chat to us after the event. Otherwise, we all give a warm welcome to Professor Brian Lovell.
Thank you, everyone, and I'm a long-term IEEE member. This year I'm the chapter chair of the computer section, so I will be organising some talks and so on, but I've been, it's a great organisation. I thoroughly recommend being a part of it, and it's, I've been with the IAPR and the IEEE, but both societies are fantastic. This is a summary of some work. I'm still working on this in the face recognition space, but mostly using artificial intelligence. For those of you who are engineers anyway, I'm teaching fast AI version of artificial intelligence in my 4630 class. I'm trying to bring it into the 4620 class as well, so we can do some AI there. But basically I'm using exclusively AI techniques. On the screen is a whole bunch of people who are not really people. So these are all synthetic faces. So these are some of the ones we've been generating. And so I'll tell you why we're generating artificial people. One of the big issues is privacy, because we want to use faces, but to use faces, real people's faces, we should get their consent. And we don't need consent from these guys. I've got an ethics exemption for using synthetic faces. So I can do stuff with these faces that I can't do with other faces, like human faces, to the same extent because of ethics requirements. And it's very hard to work in the field of face because that's how we identify each other. So they say you have to make it not identifiable, but face is your identity, effectively. So take a look at this. I'll tell you a little bit about work we've done in face and how it's evolved over the years and sort of what we're looking at right now. I will also mention I'm very, very interested in getting PhD students and building up the group in this and other areas. But we're doing a lot of work with Sullivan Nicolaides pathology at the moment and trying to roll that out across Australia. And we're getting them to fund some scholarships and put on a research fellow, this sort of thing. That's pretty exciting. Also talking to Novartis, the big pharma company, one of the nice ones that doesn't do vaccines. And they make a lot of generic drugs which are fairly cheap. If you ever get antibiotics, you've probably seen the brand Sandoz. That's part of Novartis, so they're the generics you get in all the chemists. Anyway, they're quite interested in this work, and everyone's interested in AI just worldwide. It's the basic lifeblood of modern industry. So let's take a look at some recent work on face biometrics in the UK. I don't have anything happening in Australia, but I work in the UK. There's deployments in that country. I did electrical engineering and computer science, both at UQ. If you ask me who I am, I'd say I'm an engineer, but I do work mostly in software. And for that reason, I like to build things. I like things that work. I don't like, I suppose, doing stuff for its own sake so much. I always sort of think of how can you use this, how can you do something with it. And I love to see working systems and that can actually be rolled out. Because if they don't work, they don't really do anything useful for anyone. So that's my bag. And so we've been looking at systems that have been deployed in reality, and we've had to face a lot of real world issues, which sometimes result in quite good research. So I like to work on real things, and the second catchphrase is it's even better if these things are deployed in pubs and bottle shops. So that's a big achievement in life. And so what's happening is in many countries they've got a huge problem with shoplifting. Shoplifting is not a major crime, and it's very hard to get the police to do anything about it or even to prevent it. My wife had a handbag stolen in Paris, and the police, unless somebody's dead, they don't give a damn. But we sort of had to get a police report to claim the insurance, and nobody wanted to fill all that paperwork in because they're not going to do a thing about it. Okay, so but if you're the person who's lost their purse and all your identity documents and everything, and you want to claim your insurance, you need that form filled in. But it took me, they wouldn't fill it in at Paris airport, they wouldn't fill it in, the police wouldn't take it, they pretended they couldn't speak English. And I went down, I had to get a Frenchman with me to accompany me to the station so he could fill in a report, and I eventually got it filled in, and they were sort of I knew they were trying to get out of filling in the paperwork, and they said, oh, that handbag, was that yours, sir? I know what they're going to say. If it's not my handbag, my wife will have to come in and do it, and I've spent weeks trying to get this report done. And so I said, yes, that's my handbag, you know, because otherwise they wouldn't fill the form in. Anyway, so they have big problems with this in many countries, and even in Australia. My virtual son-in-law, because I'm not quite married yet, he runs an Aldi store, and they have people stealing things all the time. And I asked him what they mostly steal, and he said, it's mostly meat. I said, meat? And then I just noticed on my slides, first thing mentioned is meat. So people steal meat, nappies, razor blades, deodorant, etc., etc. And what happens in his store is people get a great big slab of expensive meat and stick it down their pants or wherever and walk out with this stuff. And the storekeeper can't really do anything because they're not a policeman. They can't, you know, interfere. They know what's happening. But it feels really bad if you're working in a shop and people are stealing things all the time. And it depends a lot on which area you're in. So if you're in a nice area, generally you don't have as much problem. If you're in a pretty grotty area, and my sort of son-in-law has moved to various areas, and the shoplifting varies depending on where you are. So if you're in a bad area, this is really bad, and it's really bad for the people working in those stores. So this is somebody, he's running a bottle shop, NISA. It's a string of bottle shops, and they installed face recognition, and this was to identify potential shoplifters. So people who have I suppose, recidivists, people who come back and keep doing it all the time. And they can't get the police involved, but if they can identify somebody who's likely to be stealing things, they can basically give them the evil eye and hope they go away. Okay, and that sort of works. Once people know they're being, I know you're going to do something, then they go elsewhere where they're not recognised. So let's see how this goes.
Hi, my name is Chirag, and I'm the store manager at NISA Local Borough. Before we had FaceWatch, we were struggling to manage crime in our premises. But since we've had FaceWatch installed, it has made a massive improvement and our crime levels have dropped drastically. So FaceWatch is super easy to use. It's very user-friendly. It takes less than a minute to report a crime that's occurred in your premises. And once a crime has been reported, it is instantly put onto their servers. So next time the offender comes to your premises, you get alerted instantly, so you get all the information that is required for you to know exactly who that offender is and stay on top of it so the crime does not occur again. The staff really like it. It's a vital tool, and frankly we'd be lost without it. The customers love that we have it because it makes them feel safe whilst they're in our premises. The installation process was quick, tidy, and it was very professional.
Okay, I was trying to figure out how to pause that, but I didn't succeed. There's a box there. I just stopped there. I was trying to get to stop on that frame, so I'll repeat that. But there's a box on the wall. That's our box. Okay.
Hi, my name is Chirag, and I'm the store manager at NISA Local Borough. Before we had FaceWatch, we were struggling to manage crime in our premises. But since we've had FaceWatch installed, it has made a massive improvement and our crime levels have dropped drastically. So FaceWatch is super easy to use. It's very user-friendly. It takes less than a minute to report a crime that's occurred in your premises. And once a crime has been reported, it is instantly put onto their servers. So next time the offender comes to your premises, you get alerted instantly, so you get all the information that is required for you to know exactly who that offender is and stay on top of it so the crime does not occur again. The staff really like it. It's a vital tool, and frankly we'd be lost without it. The customers love that we have it because it makes them feel safe whilst they're in our premises. The installation process was quick, tidy, and it was very professional, and the good thing was they didn't get in the way to disrupt any business. The information added to the database is shared to the local area, benefiting the community. If you're considering FaceWatch, I would highly recommend it because it is a massive deterrent for any crimes that may occur within your premises.
So FaceWatch does installations in lots of stores, hundreds of retailers around the UK, and they recognise that they have a recognition service, also an entry service, so you can put a face into the system, say what's the problem with them, and when they turn up somewhere else, you can be alerted this person's turned up and what they tend to do, like stealing. There's a lot of people come from other countries like Romania, and gangs come across to the UK and they just hit a whole bunch of stores taking women's handbags and various things, and the police really don't give a damn. But it's very bad for the retailers. It's also very bad for the people, for example, in the pub. You go to the pub and your handbag's stolen. And you've got all this stress, you haven't got any money to get home in the cab, you talk to the security and so on. So part of this system allowed you to do complete police reporting at the station. So they get all the witness statement and everything from the person through the security guards, and they file it, and you get a police report back that you can use for insurance rather than having to go to the police station. So it's all sorted out just after, say, your handbag's stolen or whatever the incident is, and you can just get on with your life and claim your insurance. But it also tends to act as a deterrent. So it's quite an interesting model. There's been quite a bit of fuss in Australia about using face recognition in Kmart and other places, so people have been experimenting with it and they don't tend to like publicity, and it's probably for the same sort of reasons. But in the UK it's been adopted reasonably well, and I'd probably guess there's a lot more shoplifting in the UK than there is here, so we've got a fairly, I suppose a fairly good society here, that there's not a lot of just local crime and so on, but in the UK they do have big problems, and same in the US, as you probably know. Anyway, so that's great, and we've continued to work on this technology. We won the, in 2021, we won the Home Office Prize in the UK with our Galahad software for best face recognition system. So that's sort of where we are now, and at the moment I'm just getting some new algorithms tested by NIST, so I'm just about to submit those and see how they perform. Now, this hasn't come out of nowhere, and this is a very complicated area. So we've been working in this space for a very long time. So in 2011, we had a system working with multi-user recognition, etc. And this is a video from a few years ago, 2011 or so, walking around the corridors of GP South and having everybody being recognised on the system we had then. And the systems we have now are completely different from those. But that was something where we won a lot of awards back in 2011. And this is before deep learning. Okay, so it's recognising all those people. Performance was pretty good. It's much, much better now. And as I said, this was pre-deep learning. And had a nice group there. We were actually working within NICTA doing this work at the time until NICTA Queensland shut down, but I've continued doing it because there's been a lot of interest. We won the IFSEC award. So IFSEC is International Fire and Security, which is a big security show, and we won the award through a partner of CCTV System of the Year for face recognition in a crowd with basically that technology. We also won the Awards in Queensland and nationally, and we won the International Awards for Best R&D back in 2011, so that was a good year. Okay, our systems had been commercial. 2011 system was pretty much as you saw it there, was deployed at University of San Francisco, and it was used to manage all the dormitories and so on. So they had a problem that people came into the dorms, and you had to be a resident of the dorms to come in there, especially after a certain hour, and they'd have like 5 people lined up at the door, and they'd use the video to recognise the people and check that they were students who were resident in those dorms. So, because you had a problem that one person would open the door and then you get a whole bunch of tailgaters coming in, so they're able to look at everybody, identify them just through the video, and then say, that's fine, they opened the door. Okay. So it's one nice application. But things have to work better. So one of the problems with the system back then was the face detection bottleneck. And it turned out that our systems were running 98% of their CPU time was in face detection, 2% was in face recognition. So the detection was the big problem, because with detection you have to check the whole frame and you have to run at 25 frames a second, to stay real time. And that was using up an enormous amount of power. And so we had to put that onto a GPU and so on. But it wasn't the recognition part. And the recognition part can be done in funny time, because once you've pulled the faces out, you can then recognise them later. But if you can't pull them out in time, you've missed them, if you don't keep up with the frame rates. So that was a problem, especially since they tend to use huge cameras with 5 megapixel cameras now, and they often have 20 or 30 of these things. So you really had a very big load with the face detection. So that was something we were working on. The other problem was with face detection back then, we were using cascade detectors, like Viola-Jones type detectors, and they were not, they could only really recognise faces that were frontal. So, and about 15 degrees from frontal. They couldn't recognize faces in larger angles. And a lot of the cameras capture people at 90-degree angles. So, so what we said was the first problem we were addressing was a choke point situation. Choke point is like you get at the airport where everyone's coming off the plane and everyone's walking straight ahead and you can sort of see their faces. They don't read their text messages and things because if they do, the rest of the plane passengers will, push over them or, So everyone's sort of walking fairly rapidly and looking forward, and that's a great way to get faces. But you find as soon as people stop looking at you, they're on their phone and they're looking down, you can't really get their faces. And that's a practical problem. So you think, a queue at a shopping centre would be great, like going to a movie theatre, great place to collect faces, but everyone's on their phone. So you have to find special opportunities. So we wanted to widen that, and so we started looking at the problem of the face in the milling crowd. And this is like the cocktail party, recognising people in a difficult circumstance. So you have a real problem with what I call face harvesting. So people just don't look at the camera, so you can't do their face recognition. And you can do things like you look at a choke point situation, that works. If you have a big sign, it can be in a tractor and people look at the big sign, especially like in Roma Street Railway Station where we had all the trains, people go and look for their train and you get a good view of their face. But in general, they're very hard to do. And a lot of people are moving. So, they're walking and so on and you get motion blur. A very good place to collect faces is when somebody opens, say, a glass door, because they stand there and they look at their hand, grab the handle and pull, and if you've got a camera there, you can get a pretty good shot of them because it holds them still, plus they're looking at their hands so you know where they're looking. So you have to figure out where to put your cameras. But okay, if you haven't got control, that's our situation here. And so we could handle error bridges, borders and concierge situations. So concierge situation is where you're talking to somebody at a desk and you have the camera over their head and you can just, like a passport type situation, that works. But it doesn't really work in cocktail parties, conferences, shopping centres or check-in areas. So what we wanted was much better performance, but the cascade detectors that we were using at the time, which were about 10 years old, but they're quite good, they couldn't cope with very large changes in pose, for example. And so we wanted something better. And because of the huge computational requirements, for many years we were stuck with cascade detectors, and the idea of doing face detection with a neural net was just crazy back in 2012 or something. It was just far, far too slow. But that's all changed, and they've become very fast now, and the GPUs have got bigger. So at some point there was a crossover, and using deep learning was very attractive. So, so what we wanted to do was to get be able to detect people at very wide angles. We wound up, instead of the system being a CPU with GPU accelerating it, the system then sort of turned inside out, and we actually had the CPU as the main processing element driving into the GPU because we needed that very high speed. And so there's an architectural change. And we also wanted very, very high frame rates because we wanted to process not just one camera stream, but maybe 10 or 20 camera streams. So instead of doing 25 frames per second, we might need 500 frames a second. And we actually achieved that on these nano devices. So we could do, 2022, we're doing 500 frames per second on a nano, which is quite cheap compared to a PC. And as far as I know, we're still the only people doing face recognition on embedded devices. So rather than a PC, we've got our own little box that does the face recognition. So here's the box. So this is face detection at the edge. We have a box with 0 config. You plug it in and push a button to restart it, and that's all you have to do to get it running. So no PC, no keyboard, etc. So there's nothing to screw up. So when we did a comparison against Cognitech and these other companies, they took in about 1/4 of a ton of equipment of water-cooled PCs, and we took in a box that you can virtually put in your pocket. Okay, so other systems use PCs and GPUs. We've put the whole thing effectively onto a GPU, and the software is all downloaded remotely from a server. Here's the sort of things we wanted to do, and this is some early work we did on faces in a milling crowd, just to show what could be done. So notice here, we're not recognising everybody because we don't know who they are, but certain people, that girl's, what's her name again? She's a Princess Diaries. Sorry? Who was it? Hathaway, yeah, I think that's Anne Hathaway, and so you can see there's a little face there to sort of show the match. So this should run, And you can see all the boxes there, the detection boxes. They've got other famous actress there, Meryl Streep, that's right, and Brad Pitt, such Angelina Jolie. But notice the very wide angle, Sandra Bullock. Okay, that's Hermione or whatever it is from Harry Potter. Yeah, so this shows you what can be done, and that's pretty good. Oh, that's Russell Brand, yeah. It's a while ago, this video. So it's a bit hard to do surveillance video, so this is sort of similar. It's a Hollywood type scene. Fairly good quality, but these people are all recognisable. This guy's pretty good, so he's matching that blue genie. That's Will Smith. The one. So there's some quite interesting detections here that were quite difficult. Oh, this guy too, he changes weight all the time. I can't recognise him from his Christian Bale. Yeah. So it's detecting a lot of people but only recognise. So look at Julia, she went right out of focus there and it's still tracking fairly well. Lady Gaga. Yeah. So that was using a, now what was that using? It was using MTCNN, which was a deep learning method, and that could actually process video at a fast rate. MTCNN's dead now. We're using, what is it, retina face, and then there's something beyond retina face. So that this area is improving all the time. The tech's improving. You can see sort of difficulties with some of these shots. You can see here you've got Julia Roberts, and she's quite. Face is obscured and so on. I'd have trouble recognising her in those conditions. And same for a lot of these people. You see this guy, he's matched against a photo where he looks like he's bald and has no hair, and now he's got a beard and moustache, and there's a good match there. So that's all fairly good. And it was one thing to show a video because it always works on a video. It's another thing to get this working in a real sort of environment. So that's something we'd worked on quite a bit to get the next generation of technology. So let's take a look at deep learning methods. So since 2015, deep learning shown great promise in face recognition, and basically there's nothing touching it now. So you're always looking at deep learning solutions, whereas that old one I showed you was using bag of words, bag of features type methods, which worked okay. It was actually worked remarkably well, but error rate was still far too high. So these things, the error rate's really, really low. And one of the best is ArcFace, and it's still quite competitive in NIST. NIST is the big National Institute of Standards and Technology in the US, and they do face recognition testing, and you can't sell face recognition in the US to a government agency unless it's gone through NIST. It doesn't have to perform well, it just has to have been tested. So, we're doing a NIST test at the moment, which is a pain in the neck. And what's interesting here is looking at ArcFace, is ArcFace, you can use the R100 refers to a ResNet 100 backbone. So we're just going to look at the R100 so that they're all the same. And the only difference between these three lines, red, green and blue, is the data set. And you can see that first off, you can see the performance here. I'm trying to think what's the best column to look at. Well, you can see here it's got ArcFace. It's looking at masked people and looking at the performance. And it's looking at children, Africans, Caucasians, South Asians. What's a South Asian? Any idea? Yep. Yep, Indians. Okay, not American Indians. Okay, so basically South Asia, so Indian Asians, and then the East Asians are the Chinese type Asians. So that's how they're described here. And then it's got overall performance. But notice the overall performance starts out at 80%, which is pretty bad. 1 in 5 is missed. Then the next one we can see here has gone from 80 to 84, which is actually a big improvement because remember it's the error rate we're worried about, so it's quite a big drop in error rate. And what's the difference? The difference is the data set. And you can see here that this uses the CASIA data set, which is a Chinese sort of data set. This uses a much larger data set. And then this one down here is using Glint 360, which is much larger again. And the detection rate goes from 84 to 90. And then if you use a private data set, which probably means they're using data they're not supposed to be using, like surveillance data, it gets up to around 97%. But we haven't changed the algorithm. We've only changed the data. So in this case, ArcFace, the algorithm, anyone can use it for any purpose. But if you use the data set, if you have a pre-trained one, then you're not allowed to use it commercially. And so we've been training our own. You can train it yourself, but you can't use one that they've pre-coded, okay? And you can change the data set. And you can see from this that you can work a lot on algorithms, but really it's the data that you've got that makes the big difference. So it's the data set's more important than the architecture, because the architecture can learn, and you just have to tell it what to learn. Okay, so data sets are really important, and big data sets are better than small ones. So now around 2019, we got hit with ethical issues for face recognition. And this was sort of on the back of reports of face recognition being used to discriminate against people in China. And I don't know, what the situation was there, but there's a big crackdown because money that was spent on Australian research was being used by Chinese researchers, and it was helping the Chinese government effectively discriminate against a particular group. At least that was what the ABC was saying, and we don't know what the reality is. But then there was a big crackdown because they said, hang on, we can't have Australian taxpayers' money being used for these purposes. And they brought out this national statement on ethical conduct in human research. And that was there's always something like this for medicine, but it never really applied to computer science and AI. But now we've been brought into that area. And about the worst thing you can do is face recognition research, because they say that you have to get consent from everybody. They have to it has to be informed consent. So they have to actually know what you're doing, which is pretty hard to describe. And you need, because it's deep learning, you need millions and millions of consents. So it's impossible to collect that data. Plus, that constraint doesn't apply to anyone working in China or the US and whatever. They don't have this ethical constraint. So it was hard for me to figure out what I could do, given that I virtually couldn't do anything in this area, even though I was well known for it. So, in a nutshell, all databases collected off the internet require ethical approval. Even if it's got ethical approval somewhere else, it has to have it in Australia, and that basically means informed consent, and none of them have it, okay? No, because they're all trawled off the internet and you don't have consent. There's no ability to use data sets that do not have ethical approval. No way to bypass this. All data sets must have fully informed consent of persons concerned to use for face recognition research, and no usage of international data sets that do not comply. Stuffed. Okay. So, how do we continue to research and test face recognition systems? So, what we need to do is to find a way to create databases that either have full consent or no requirement for consent. And this came out just before COVID hit. Now, the ability to take people's photographs, even with consent during COVID, was virtually none, especially if you wanted to have a decent mixed demographic and get international cooperation on collecting a consensual database. Just getting someone in the well, I wasn't even allowed on campus, none of us were. So during COVID, we had two big problems for face recognition, is we couldn't collect databases, and also everyone was wearing a mask, so we couldn't recognise them. So that was a big challenge, and people started working on masked face recognition during COVID. So now it's not really a problem again, but that basically blew the systems out of the water, including my iPhone, because it wouldn't recognise me to open the phone. So our problem is we don't need like 100 images, we need millions of images. So collecting that database is just impossible. So one idea I had was to create a database I called Edith. I thought if people were worried about ethical research, I should have a database that's called Ethical Database. And the idea of this, we're having interactive training heads. So we'd have a prototype head, capture a 3D head and get full informed consent on that. But with a 3D head, you could actually create huge numbers of views. So if you had a 3D head, you can rotate it, do all sorts of things with computer graphics, and you know it's the same identity all the time, and you can put glasses on and put head coverings on and so on. So that was one idea, to create heads. How well it would work for face recognition, I'm not sure, but at least your ethics could be, you could meet the ethical requirements, because each of those could represent 1,000 instead of just one face. You may have heard of a woman called Edith Head. She was a very famous costumer in Hollywood. Lots of movies, King and I, etc. She did all the costumes, and so that was another thing with Edith. So that was her name, Edith Head. So that image there, one of my students, was captured using my phone to do 3D face capture. And so I did have the tools there to just using an iPhone to capture faces. And my thought was, during COVID, we could get people with those phones in other countries to contribute faces to the database, do the consent, so we could sort of do it remotely, because the devices for capture were pretty simple. So that's so you can have collect faces like that look very realistic, and you can also get those faces and throw sunglasses on and so on. So we had the ability to put on sunglasses, put on a moustache, etc., to produce a variety of faces. Now, then we started looking, that was still a lot of work, then we started looking at this idea of generating synthetic faces, because around 2018, 2019, Stylegan came out and NVIDIA showed you could create fake celebrities. And they look very realistic. And so those techniques have improved. And so we looked at Stylegan, and we did this paper, Faces a la carte, which is text-to-face generation via attribute disentanglement. So we'd put a phrase in and then generate a whole bunch of sample faces. And you could say male, female, African American, whatever else, put these phrases in, it would come up with some sample images. And so we had this idea of producing a diversity of images there without the 3D faces, but we could generate these like 1 million faces a day and use those, and then perhaps use them for face recognition. So this is where the synthesis came about. So we could do 3D heads and collect things. We could also do synthetic 3D heads and collect faces that way by turning them around in space and making different views of the person. So you could actually create views that you couldn't create with humans. For example, what we can do now with AI is I can take somebody, a human, capture them and make them into a 3D head, and then age them and change their gender and all sorts of things like that, which you can't do with a human. Okay? So, or I can make a totally synthetic face and do all those things to it as well. See how that works. So you could also create lots of surveillance data, because there's a lot of ethical issues with surveillance data, but you could simulate surveillance data, which is hard to collect photographically. So let's take a look at synthesis of a 2D image of anything. Okay. So the big technique that came out last year was stable diffusion. And that's advanced enormously in that time. So Stable Diffusion came out, which got us all excited. Then ChatGPT came out, both in 22, and they were huge advances. And we're still living with the consequences of those, but it's not stopping. It's getting new stuff coming out all the time. So let's see, how can we synthesize a face? Well, look, the way the technique generally works is you start off with a random noise vector, and you have a random noise vector, and then you convert that into an image. And if you just generate random noise, imagine you've got an image which is 256 by 256 color image, and then you've got 256 by 256 pixels. Each of those pixels, if it's 8 bits, can have 256 values. And if it's colour, you've got RGB, so you've got 3 of them. So if you multiply that number through, that's about 50 million possible values. So all the images, 256 by 256 images, are somehow in that space. Okay, so you can generate any image that way, but normally if you put noise in, you're going to get noise out. Every now and then you'll get the Mona Lisa, or you'll get Brad Pitt, but it's very unlikely. Okay, so the space is huge, and but the idea is we can synthesize any possible image by just using a random number generator. Now, the problem is a lot of that space isn't faces. A lot of that space is something else, okay, which is pretty useless. So only a small subspace, which we sometimes call a manifold, represents human faces. And the rest of it's something else. Just like in the 3D world, the 3D world encompasses the entire universe. Only a very small percentage of that universe is the planet Earth. And none of us are really sitting in the Earth's core or up in space. So it's actually only that 2D, I suppose, 2D surface of the Earth, where we're walking now, is the part where you'll find humans. They're not anywhere else. Okay? So that's the same sort of concept. So basically, if you want to find a human, you want to look on the surface of the Earth, even though the space is absolutely huge, which is like infinity by infinity by infinity, representing all 3D space. So here we want to find a subspace where every place we look is something interesting. So this was first done back in about 2012 or something, and the idea was, 2013, there, I've got the date on it. So that's MNIST. Now MNIST is basically handwritten digits for postal codes, and there was a fairly large database of that at the time, and what you could do there is you could create a space using what's called a variational autoencoder, and it's a 2D space, and everywhere you looked in that space was a handwritten digit or variations of it. So no matter where you picked a point, it would always come up looking a bit like a handwritten digit, or a lot like a handwritten digit. So you could do this with an autoencoder. You could do this, but the areas representing the number 1, number 2, etc. were far apart, and in between was rubbish. With a variational autoencoder, it made all those clusters jam in on top of one another, so everywhere you looked was a digit. And so in this one, if you just picked a random XY point, something would come out like that, which was a handwritten digit. So you've basically found a manifold, which is the handwritten digits of a certain scale, and any random point you chose in that feature space would give you a handwritten digit. Is that pretty cool? Okay, so that's the sort of thing we're wanting to do. We're wanting to find a small space that represents human faces amongst all the possibilities, and that's just an extension of this. So this is good, and that was known in 2013, and it relied upon having a, what we have was a neural network encoder, which looks like a pyramid. It takes the full-size image, keeps shrinking it down layer by layer until you've only got 2 wires, 2 parameters, a mu-x and a sigma-x, if you like, coming out. This is fed here, and then it's turned from just 2 values back, and it's resynthesized back to the full-sized image. Okay? So it's called like a U-net. You go shrink the thing down until it's only 1 or 2 values, and then you, from the 1 or 2 values, you then generate images. And so that means that you've only got 1 or 2 values in what's called the latent space, that's the hidden space, and if you choose them both randomly, you'll wind up somewhere on that picture. So if you look at a traditional autoencoder, it's going to look something like this on a T-SNE diagram. It's going to be spread out, and there's a lot of white there, which just represents rubbish. So if you go into that, those rubbish spaces, you get something that's not recognizable. But with the variational autoencoder, they made this far more compact, and so everything's sort of lying on top of each other, and the white spaces are very diminished. And so that means if you just choose a random number anywhere in that XY space, you get a digit coming out. Now, this technique was, I'll just go back one. Okay. This technique was sort of limited to quite small images, not really good enough for faces and so on. So they did a lot of work on that until eventually they managed to scale it out to much larger images. And they used what's called Stylegan or ProGAN, and there are quite a few developments along the way. How are we going? Not too bad. Okay. So what we wanted to do is to synthesize full high definition color images rather than just numbers. So some developments were there, and there's a big noise came out with Stylegan and Stylegan 2, and Stylegan 2 is just slightly better than Stylegan and better rendering, and that could produce synthetic celebrity faces. So they used the Celeb data set to create new faces that didn't exist before, and they were not of any person, they're just a synthetic face that looks a bit like a celebrity. And so we did quite a bit of work on Stylegan 2, and then there were some variants. This is EditGAN. And it turned out in that space, if you went in certain directions in the latent space, you could do things like go from male to female. You'd find that all the males were sort of down here, all the females were here. So if you went sort of in the general direction from male to female, you could sort of preserve identity but change the gender. Okay? So you could also do things like, here's people with glasses, here's no glasses. And if you went in the direction of the glasses, you could actually add glasses to a person. And these things weren't fully decoupled or disentangled, but you could still do some pretty cool things using these techniques. So the other thing you can do is take a real sample, a real person's image, and you can convert them into a number in latent space. So you find basically the point in latent space that corresponds to a given person. And the translation could be pretty good, so that you can basically turn yourself into a number. Okay? But you're sort of that already, because your face is determined by your genetic code, which is a big number. You could write it as a number. and that number says what you look like and how you look like at every age. So if we could do that translation, which is from the genotype to the phenotype, we could say, oh, here's some DNA, this is what you look like. And this is what you look like at age 5, at age 10, at age 20. So that's sort of to me, that's a little bit of a long-term goal to go from the DNA to the person's face. And I'm doing work in genetics at the moment, and that's sort of a thing worth looking at. So what you can do is you can take a real sample of a bird, for example. You can put the bird into the system, find the point in that latent space that corresponds to the bird, and then you can push it in certain directions to change its colouring and characteristics. So this was EditGAN, where you could change the images into other images with semantic meaning. Okay, so you want not just to change it, you want to change it somewhere that you can understand, and you could actually have a text command, make this male into a female or something like that and control it that way. So it turns out in this latent space, you have, in a space, it turns out you can actually work out black hair is sort of in a certain direction, and this is multidimensional space, so you can't really visualize it, so I'm only doing this in 2D. Glasses are sort of here, people with glasses, without glasses, male, female, for example, so on. So you can work out these directions. You can just put a whole bunch of males in, put a whole bunch of females in, look at the vector between them in multidimensional space, and you can go a bit in that direction. But generally, if you go too far, things don't look very realistic, but you can move a certain distance for some characteristics. So it's not fully decoupled, but it's, or disentangled, but it's to some extent disentangled, which means you can sort of change male, female, and the hair colour doesn't change, and things, so the different changes are orthogonal to each other. Okay. So this is a bit about that particular work here. We were worried about image diversity, so we wanted people to be different ethnicities, not just, so one problem with Celeb A is everyone comes out looking like they're from Hollywood, and there's not good representation of certain ethnicities, so we wanted to have more diversity. The trouble is if you force diversity, often the faces looked unrealistic, so the trouble was getting a nice diverse population like in the real world and have them all look real. And we wanted high efficiency, so our method turned out to be fairly high efficiency, and we did a lot of work in these latent spaces. So, for example, if you look at the real data, it might be distributed like that. You convert it to a latent space we call a Z space, and it looks a bit like that. And then we can warp that again to get a W space, which was done through an eigenvector decomposition, and that had better decoupling between the various parameters. So it was better to do, in this space, the edits look better than if you did it in the original space that was proposed. And so it's using principal components analysis to create a new space where things work out a bit better. And you can see, if you look at the sampling space, you've got all these different things like glasses, smiling, black, male, female, etc. And some of these things are well decoupled, other things, there's a bit of coupling still. So that's an unsolved problem. So it's improved, but you can't quite disentangle everything. I don't know how you can disentangle, I suppose you can disentangle gender and identity, but in the past you couldn't. But nowadays people can transition, and you'd have to say, is it, well, that's getting very political nowadays. Here's some experimental results, text to image. So we said here's a young male with blonde hair, and it generates some random samples that sort of match that text. Or a wavy black hair with makeup, and it's strangely made lots of women. So I suppose they're the only ones wearing makeup in that case. Glasses and hat, and you've got people wearing a hat and glasses. Bangs. So bangs is an American term for a fringe. It's this particular haircut that a lot of women have. And moustache, non-smiling. Not many women have moustaches, but anyway, so you can do this sort of thing, and these are what we call attributes, and then you can produce a whole bunch of faces that match these conditions, and that's so where that work got to. There's some evaluations, and this is synthesis in various spaces, like the original space and, for example, the Z space, and the manipulations if you use the original F space and had a certain manipulation, you could get quite bad changes to skin color and so on. If you use a better space, then you could make these manipulations and the images look a lot better. So we have to have them looking good. So we're looking at aesthetics in this case. Okay, got about another 10 minutes. Yeah, so here's some examples of changing people. These are real people, photos, turned into synthetic people. So here we have the real person, and what we've done is we've found the space we've gone into the latent space and found him basically in that space, or his twin brother or a nearest neighbour, if you like. So we can get a person and convert them into the space. And here we have a woman, and we've converted her into a latent space. So that looks very similar to the woman, but now we're in that space. We can do things like give her blonde hair, arched eyebrows, opened a mouth, pointy nose, etc. And we're able to manipulate that real person into various forms. So one of the big problems with synthesizing faces is how do we know that we're producing the same person? Well, we don't. We're synthesizing something, and it may look the same, but is it the same person, or is it somebody who just resembles that person? Because they're all artificial. So that's one of the big problems with synthetic faces, and one solution to that is to actually run these faces through something like ArcFace and determine whether they're the same person or not using a face recognition system. So you're sort of bootstrapping, because the face recognition systems are about 99.99% accurate in testing. So basically they'll do better than most humans, so we can actually use ArcFace to determine if our synthetic face is still the same or whether they've changed in some characteristic. This is still work in progress, but that's one idea. Here's the same person, and what we're doing is just synthesizing him in various angles, and you can see we've been able to turn the head, and our question is, are these the same person? And that's sort of, you know, we've got some measures up there of whether these people are the same or not, and you know, we can look at them and say they look pretty good, but we need to automate that because we want to do millions of faces. So you can use ArcFace to do that. And you know, we can produce like 1 million faces a day. You can also produce synthetic movies with digital actors, and this area has just gone like wildfire. You can produce complete films with characters who are dead and so on, and they look really very realistic. So here's another example that's hard to do in real life. You take the same person and you change all their hairstyles. Now, to do that with a real person would be incredibly expensive, especially if they were female, because it's like $300 a haircut. And you'd have to wait a long time till they grew their hair back before you could do the next one. But that's something you can do here that you can't do. So we've got this hope that even though we're using synthetic faces, because we can do these sorts of things, there may be some advantages. So while we were doing that, some person invented Stable Diffusion over in Munich there, and that took the world by storm. So I say it's probably the greatest advance in deep learning since Stylegan in this area. It was just a massive leap forward, and you could fully synthesize people and backgrounds and so on. It's already gone commercial. I mean, it's out there in Runway and Jasper and so on. So here's me having a play with Stable Diffusion. I just wrote in, make me a picture of a girl with a straw hat. And it came up with all these pictures. Some of them are sort of more like a painting. Some of them are sort of photorealistic. Okay, and that worked pretty well. And so I played around with this, and I had a more interesting prompt. I said, give me a girl with a straw hat lying on her back on a beach towel. And that's what it came up with. So here, the girl's very small. She's under the hat, lying on a circular beach towel. Here she's drowning in the beach towel. Here, I don't know what she's doing exactly, but it just doesn't seem to make a lot of sense to me what's going on. You know, here she's under the beach towel rather than on top of it, but it looks fairly realistic. So it's a little bit funny what it does sometimes. If you try to tell it to do something far away from what it's seen, it tends to do it badly. But it's amazing how good it can be. But you'd have to sort of check the output. But the beautiful thing here is you can create people who don't exist as well, in this case, just from a text prompt. Using a variant of this called ControlNet, these are people in different poses that we synthesized using AI. So these faces, we checked this against ArcFace, and it was the same person in every case, and we could get them in all these different poses. So it looks pretty impressive. Here's some more examples. And note they're the same pose as the previous image. We've basically said, here's the poses we want. How do we get those poses? We could take a photo and do a 3D map or do a canny edge detection and force these things into have exactly the same poses. So you can see each of these synthetic people are in a pose that we've predetermined. You know, look at on the bottom there, she's got her hands on her hips and so on. Pretty good, different ethnicities, obviously. And how did we create those? We just told it to create an old Chinese woman or something like that, and we gave it both a text prompt and an image prompt, which was the pose we wanted. Okay, now I've got another idea to do synthetic faces. This is a fairly new paper called data distillation, which is really exciting, I find. The idea here is that you want to create you've got a data set you can train a network on, and if you train on that data set, you get a good result. So that's pretty exciting, but you need access to that data set, and that can be a problem. And sometimes those data sets are very large, but you don't actually have to have them so large. So what they suggested here is you do trajectory matching. So when you're training the network, if you think of a network as a set of, say, 1,000 parameters, a network can be represented by a point in a 1,000-dimensional, multi-dimensional space. Okay? And so that point, as you're training it, that point moves on a trajectory until it eventually gets to a point where we say it's trained. So we could have that same network, and what we can do is we know the trajectory points from training, and for each trajectory point, we figure out what database would get us there. Not the original database. In this case, what they've done is for this example, they used a database that was 1/10 the size of the original data set, but it makes the network go to the same place, so it gets to the same training point. And so it's actually creating a new smaller data set that has the same effect as the big data set and gets you to the same point. And the good thing there is, at the end of the day, we don't care about data sets. We only care about networks. We want a network that it has learned very well and does a good job. But we don't care about the training set. It's just a way to get there. In this case, we do data distillation. We train it there with a big data set, and we get a good network. And then we replace that big data set by a small network that gets to exactly the same point, but it's much smaller and faster to train. So this is the idea here, which is data distillation by matching training. But the good thing in my case is it produces synthetic data that doesn't actually look like faces, but it still gets you to the same point. So you can have a network, you've trained it on real people, and then replace that with a whole bunch of synthetic people, and it will train the network to the same point. So that's perhaps because the problem with generating 3D faces and synthetic faces, they look photorealistic, but is that useful? I mean, do we need that? Maybe we can use these things that don't look photorealistic and they do the same job, but they're still synthetic, so there's no ethical problem. So if you look at these, I'll try to explain the image. So this is on CFAR 100, which is 100 different classes of object. And the original data set had things like, if you just look up the top corner, that's where I am now. Just look at this one here. See, it starts as an apple, okay, or like it's actually 3 apples. And what happens is, as you train, it replaces that with a synthetic apple. Now it's only 1 apple, but when you train the whole system using this new data set, it gives you the same quality trained network as using the original. But the funny thing is that these images don't look real. So who says you have to use real images? Why not use, it doesn't matter what the images look like as long as they get you to the right point. And now you've got a whole bunch of things that don't look at all real, and they're obviously synthetic, but your system is now trained on synthetic data. So we're looking at that one now, and I've got a few students looking at this technique and postgrads and things. So we're looking at all these different ways we can get around the problem of learning, but it's also very interesting because we're into this space of creating images. We're not just doing them to make the images pretty, we're doing them for a specific purpose to basically train face recognition networks. Okay, so I'll almost finish up there. So here's an unexpected real-world face recognition challenge that we got sent some time back. So this was in the FaceWatch system, and somebody came in. Somebody came into the shop with a dog, and it gave a fairly good match to this guy wearing a mask. And while we sort of accept these things as saying, well, sometimes it gets it wrong, but when a human looks at that and says, how the hell could you mistake that guy for a dog? And you really undermine the system in terms of their faith. Because even though the error rate might be low, if the errors are egregiously wrong, people start to say, hang on, the system's garbage. Look, it made this error. And it might have been 1 error in a million, but it still made the error that a human wouldn't make. Because the trouble is we've got really good pattern recognition, and we're supercomputers ourselves, and a mistake like that we see straight through it, even if our average performance may not be better than these systems, and it isn't. So that says, and the comment was, well, that puts us in the doghouse, doesn't it? So luckily they intercepted this one, but if you don't have a human in the loop looking for these sorts of things, you could get quite heavily embarrassed. It was like we had a gender detector, and at that time Julia Gillard was the PM, and so I'd never turn that on if there's somebody comes up, because if you tell a woman she's a male or a male they're a woman, I mean, they're going to say, that's terrible. But most of these systems can't tell men from women very well at all, and for humans it's pretty much life and death knowing what the gender of the opposite sex is. It's the first thing we do before we do anything else. We try to identify that, and without names, anything else, we look at somebody to say, are they male, are they female, what's their age, etc., etc., before anything. And if we can't figure that out instantly, we sort of sit there puzzling for a very long time trying to figure out what we should do, because if you address somebody you have to say he, she, etc., or they'll get very upset, and you have to get that right. Okay, so that's about it. It's an hour talk. There's a lot more. I could talk for days on this, but anyway. So I was saying with getting errors, these outlying errors is very, very bad. And that's one problem. It's like what they call a trolley car problem, that if you've got a self-driving car, if it does pretty well most of the time, but every now and then it just runs into a set of pedestrians during a Christmas parade, that's not good. And humans are pretty robust to these sorts of things compared to AI. Okay, I won't go on here. This is all about the human ability to recognise faces, which is quite interesting. It turns out that we are very good at recognising our wives, our relatives, and so on. We're not much good at recognising strangers in comparison to these systems. So, if you see your partner, you'll recognise them anywhere, far away. But the problem these systems have is just using the photograph, and they've never seen any of these people before. So it's actually a very different task for humans. And we tend to think we're great at recognising because we're so good at recognising our friends. And they're actually pretty good at recognising celebrities. And that's why I show celebrities, because people can recognise them. But we're not very good at recognising strangers in a lineup. So, that's about it. I think I'll just stop for questions. As I said, it's a very interesting area. It's moving so fast. And every day I just feel being left behind by the development, because there's just so much happening in this area, and there's so many new things happening. Even today I was looking with large language models. Somebody had a paper there and they're proposing watermarking. So what they do is they change the probability of certain words being used and use that as an indicator that AI generated this, and like a digital watermark, so you can easily see if something's come out of an AI, because you look at the signature and it's made by an AI. So there's all new stuff happening all the time. There's usually a question on the ethics of face recognition, or using it at all. Yeah.
So I have I think, weird question. So with that amount of combination that you can do with airs, genders, stuff like that, would there be any possibility that the synthetic faces that you have created is actually a person in the room?
Yep, sure. Yeah. People aren't that unique. I used to think there was a very large number of faces, but it turns out there's not that many faces around, and they do repeat. So if there's a site called Twin Strangers, and it's interesting. You've got two people who look absolutely identical, but they're not twins. They're totally unrelated to each other, but one might be a foot taller than the other, and that's interesting, because that means a significant part of their DNA that determines the face must have been the same in both cases. And the very fact that there's quite a few of these twin strangers indicates to me that the number of possible faces is probably much less than I had thought. I used to think it was like infinity and it'd never repeat, but it does repeat. So the chances of doing a real person, obviously, you can see I can find a face that looks almost identical to anyone in this system. So that you can easily pull faces out of the system that will resemble a person, but there's no link between the person and the face, because it's randomly generated, but occasionally it'll land on somebody real. And if,
you wouldn't possess any ethical issues?
No, it doesn't. If it looks the same as somebody and you've never seen that somebody, it's not a problem, because it's not a photo of them. They can't give consent because it was created independently. But it could absolutely resemble a real person. Yeah. and it should.
For example, if you use this for an advertisement, you're using the face of this person.
Well, if you use it knowingly, yeah, that would be a problem. If it's unknowing and you happen to use somebody who's virtually a twin of somebody else, then they could argue, but they can't say that it's my photo. It just happens to look like them. So I don't know what would happen there. I mean, it's probably not a big issue, but I don't think there could be. You might have to take it down, but it's not like you've done something unethical. Yeah.
Back in the slide where we were stating that there are sort of different dimensions for different things,
Yeah.
like specs have a different dimension and the case have a different dimension, and if you move in certain dimension, you will achieve that goal moving forward. But like as we're discussing in this manifold space, so my question is that is the manifold space Euclidean? Like if it is Euclidean, you can move, but if it's not Euclidean, like if you move in that space, that won't be giving us the result that we desire.
The space tends to be latent space tends to be Euclidean. The reason is the network tries to find a simple mapping, and the simplest mapping is to a Euclidean latent space. So I don't know that there's any theoretical guarantees, but it seems that because the original space is all crumpled up, and like of faces and so on. So the example I like is if you've got a nice sort of space we'd like to work in is a space that's flat and Euclidean, and like a sheet of paper. But if you get a sheet of paper and you crunch it all up, that's the space we're presented with most learning problems. So it's like a totally squished up thing. The other analogy I like, and it works with disentanglement, is have you ever got Christmas lights and put them in a box and you pick them up the next year and they're all tangled, or some jewellery? And then you spend hours trying to unpick this thing to get it into a nice straight line. And that's sort of what the neural nets are doing for us. They're taking a space that's non-Euclidean, very, very tangled, and untangling them. And then once they're untangled, you can do all sorts of things with them. So we're sort of trying to make that space more natural and well-behaved. And that's actually getting an uncrumpled bit of paper and you uncrumple it all. In fact, say if there are two-class classifiers, the example that's often given is you have a blue piece of paper and a pink piece of paper, put them together and then crumple it. And they're the two classes that you want to separate. And the neural net basically untwists it all and produces the two sheets separate again, and then then you can make a very easy classifier. And because you can make an easy classifier, that classifier will be just like a Euclidean, so each dimension will basically represent some property. Yeah. Yeah. We haven't used transformers. I mean, they're very good for classification. Haven't used them in this context, not because it's a bad idea, just haven't. Yeah. Yeah. Generally, you train it, you have the image and the text string. So the Celeb A data set actually had text strings for all the images, like a description of the person. And we actually got flagged for doing something that was unethical. It was really funny. It was during that Black Lives Matter time. And the Celeb A had somebody from Hong Kong or whatever had annotated all these photos and said, this is an attractive woman, blah, blah, blah. And we did a subset of those, and it was... there was somebody who was, an ugly woman, something or other like that. That was actually the text from the database. And even though these weren't real people, these were synthetic faces, somebody said, oh, you can't call this person ugly. That's offensive and unethical. But it's not a person, it's a cartoon. And I thought, oh, it's a cartoon, so who cares? And that was the labeling from the database. And we had some people, like some Asian people or something in the database, and they're saying, oh, aren't there any attractive Asian people? Because we only had a subset of images there, and basically the person writing it, the main author, was Asian. Sort of, but it just got caught up in that whole Black Lives Matter thing there and virtue signalling, and it was really funny because we'd actually got full ethical clearance for the thing. It was just it seems funny because they look like humans, They're no different from Astro Boy or something like Snoopy. They're cartoons effectively. They're not real people, and yet you can't. If I said that Snoopy's got a big nose, I wouldn't get called a racist. But because these were people, because these look so much like people are saying, "Oh, you're criticising a real person," but you're not. These are synthetic images. So you still have to be a little bit careful, and you get some surprising attitudes. But so these things, you can't tell them from real people. And that's why if you can't tell them from real people, why can't we use that for face recognition? Because you don't have to there's no one to get consent from, and I've got an ethical clearance for that. Anyone else? I actually quite like the face recognition technology, and I love it on my iPhone for convenience. It means you don't have to log in. I tried to buy Paul McCartney tickets the other day, and I had to have so many passwords, Frontier Touring, Ticket Tech password, etc. And by the time I looked all this stuff up, I'd lost the window, and I had to start the whole process over again, because trying to authenticate myself to the system, because the system was running really slowly because there was a big load on it. And the beauty of your phone is it knows who you are quite securely, and it lets you straight in without any authentication process. So basically your phones can be very secure, and the Apple system is very good. The Face ID system, it works in the dark and everything. But it's so nice to be able to get into a computer and just look at it and you're in securely, compared to, hey, you always have to log in and remember all the passwords and change the passwords and then have two-factor authentication. It's so much easier just to look at the device and it lets you in. So there's a really good use. Forget security, forget all that counter-terrorism stuff. Just think of the convenience of being able to just walk up to a device and securely log in without authentication. So that Apple, what they've done with Apple is fantastic. Of course, they've monetized that. They're using it for payments and everything now. And instead of having to have devices everywhere, I mean, everyone actually carries the device with them. So you don't have to, people buy them and then they can use secure biometric authentication for any transaction. So, it's coming. There's a bit of a setback, but faces are recognising people by face is really important to us as humans. It's important when you go into your house. Even your cats and dogs can recognise you. They look up and say hi, and your wife sometimes says something nice to you. But it's very much part of the human condition. And most things you look at, cars and so on, they don't recognise you. You have to log in, use a key or something like that. So, face does give you that ability to just do things very simply. And you can verify, like I can tell who people are just by looking at them if I recognise them, and I can remember what joke I told them last and not to tell them the same joke again, what message I have to give them, etc. And basically your face radiates your identity, and we use that as effectively a login process in all our social interactions. So it's a really, face is really important, and that's why it's always been such a big activity in computer vision. And now it's just accuracy through the roof. It's really good. So, and that's why people are complaining about it, because it's really good. If it didn't work, nobody complained. Okay. So I'm sure you've got other places to go to. Is there anything else? Yeah.
Based on your argument, so for instance, under this time, when you create a synthetic face and also the human face, is there any difference, a big difference between the synthetic one and the real one?
Well, you've seen them yourself. They're pretty, they pass as being an accurate description, and the technique's getting better all the time. So even now they're good. So with more comprehensive spaces, you basically have any face in that space. But then what would be interesting is to map that, instead of just having a random number determining your face, if you could map that back to the genetics, to your DNA. And then, so if you saw the DNA, you could actually theoretically convert the DNA into a latent space and reproduce the face. And then maybe age it and change the hairstyle and everything else, things that aren't genetically coded. Sort of possible. But we were able to solve problems that were just impossible a few years ago. I mean, my class earlier this semester, there were 10 different types of animals, and they were classifying them with very high accuracy, and that nobody could have done that in the world 5 years ago. But now students can do it with a short course. So amazing stuff. Okay. Wrap up, go to my next meeting. I think my next meeting's on already.
Can we give a round of applause for Ryan, please?
Thank you all for coming. Lots of fun.
Yeah, I'm only first year engineering,
Oh, yeah.
so I really am not very qualified. I was wanting to learn about how to do some small computer vision projects. What would you recommend? OpenCV or something? Or?
OpenCV's got a bit of deep learning, and I'm using Fast AI now. I think that's really great because the guy who wrote Fast AI is a friend of mine, and I talked to him earlier today. So it's a great resource to have the person who wrote it actually online. He's a professor here. So.
Thank you very much.
Okay.
Hi,
Hey, Dan.
Hey, I'm Rachel. I'm
Hi,
the
Rachel.
president of the
Oh,
Computer
yes.
Society.
Mhm.
Yeah. So yeah, we were just wondering because we've obviously recorded the
Yep.
your talk, but we weren't able to get any of the the visual stuff.
Slides.
The
Yes,
slides.
I've recorded it here, so I'll have audio and so on. I can send that to somebody, rather Darren or
Oh,
something.
that's awesome.
I did Echo 360.
Oh,
So we'll have an Echo 360. Huh?
I have no idea how Computer 360 works for me.
Oh, well, I don't know how it works for you, but this goes straight into Echo 360, so it gives good voice. And so I'll send you the link.
yeah.
So
Very
we've got
awesome.
that. If you want a redacted version of the slides or something, that's fine.
Yeah, I mean, we just wanted to copy the slides, but I reckon we could just download the Echo 360.
Yeah, it should come to me.
Upload it to
It's-
YouTube.
Yeah.
Amazing, awesome. Well, yeah, thanks so much.
Thank you.
pay sponsorship money?
No, I'm pretty sure they pay sponsorship and
And hackathon?
hackathon
Okay.
incentive.
Okay. So in that case, just then talk, bench, and judge, and
Obviously, what would be if
we, okay, I recommend we try.
wait now where if I'm not yet done. Whoops. Yoinked. What they did was they took the laptop.
Oh, okay. Here it is.
Yeah. Will do. Well, thanks for coming to stream, Elias. This is, you can see. Hey, you know what? We got it up and running.
Yeah, did stream, but the recordings exist and it'll happen.
Oh, did it not stream?
No,
Okay.
because Bessie just started and we didn't get time to connect things up properly. I'm just like,
Yeah. I mean, I think because he's a lecturer, so probably just treated it like a lecture.
yeah.
Which is cool. I'm pretty sure I sat next to him on the TNL forum.
I'm so impressed by the borderline racism that time.
That was so funny. Holy shit. I mean,
Wow.
like, fair enough. We're talking about facial recognition.
Yeah. I mean, I didn't think about it, but that was an experience.
Like, yeah, 'cause I guess, you know,
Yeah.
the thing about facial recognition is that there is more than that. Like, okay, can you tell us your Asian stuff?
Yeah.
And then you're
This can get, wait, where's the cable box? Why didn't we just bring that?
So you didn't grab it.
Okay.
They wrote the
Put this
boxes
in there.
individually.
What the cable